Good afternoon, everyone. Good afternoon.
Good afternoon.
I was waiting for guys, but
Good afternoon, teacher.
not showing up. Let's get started. We won't wait for them for so long. So we last time discussed photoelectric emission, and we discussed the laws of photoelectric emission. We also went ahead and introduced Albert Einstein's photoelectric equation. And in that regard, we also went ahead on trying out some examples on how the photoelectric equation of Einstein can be used to solve problems. So I'll kick off right from there. If you go to the WhatsApp group we designed, you'll see that I managed to send some numbers there a few minutes ago and some notes concerning photoelectric emission. So you can always merge the notes and see how best you can have some of those questions that you come across handled. I'm here to start publishing or sending you some questions on physics. There is a paper here from MOOC I have, and according to it, I'll send some of the numbers. They have some concepts of work function and photoelectric emission. There is a number 9. I'll send it through right after this lesson. So with that, you will see that we are in position to handle some of those cases. Now, since we had earlier on seen some numbers, let's kick off from there as other people join in. And an example I want to give, example reads as follows. The question says, when light of wavelength 5.9 times 10 power negative 7 meters is incident on sodium metal, electrons. Those who have WhatsApp, I've already sent the number, that's page 90. Electrons of maximum kinetic energy (1.7 times 10 to the power negative 20 joules) are emitted. Calculate the maximum kinetic energy of the electrons that will be emitted by sodium metal if illuminated by light of wavelength 4.5 times 10 to the power negative 7 meters. So here is a number. It says when light of wavelength that is illuminated by, when light of wavelength that is incident on a sodium metal, electrons of maximum kinetic energy that are emitted. Calculate the maximum kinetic energy of the electrons that will be emitted by a sodium metal if now it has been illuminated with wavelength of that. Now, the first thing is we need to know the equation very well. The equation is HF is equal to work function plus kinetic energy what? Maximum. Now, in this case, we don't know the work function. Then they have given us wavelength, lambda 1, which is 5.9 times 10 power negative 7. We have C, which is speed of light, which is 3 times 10 power 8. Then we also have H, which is Planck's constant, which is 6.6. Planck's constant is 6.63 times 10 power negative 34. Now, when you simplify the whole of this equation, it becomes HC over lambda, because frequency we saw as C over lambda, is equal to the work function of the metal plus the kinetic energy maximum. The work function of the metal, as long as you're still on the same metal, it will not change. So that's why we need the work function in the second part of the question. So according to this, we can get work function from HC over lambda minus kinetic energy maximum. So according to what the question has given, we shall have 6.63 times 10 power negative 34 times speed of light divided by the wavelength, which is 5.9 times 10 power negative 7, minus the kinetic energy maximum. When you subtract off the kinetic energy maximum is, it was given as 1.7 times 10 power negative 20. So when you press the calculator, can we get the value of the work function? Because it's energy. So you shall get its SI unit as joules. Answer?
(3.2012 exponent negative 19).
Exponent negative 19. Now, having gotten the work function, the question said find the maximum kinetic energy. We are looking for kinetic energy maximum in the second case when we have been illuminated by light of wavelength, which is 4.5 times 10 power negative 7 meters. So with this, we shall have HC over lambda is equal to work function plus kinetic energy maximum. But this time around, this is lambda 2. So we shall have 6.63 times 10 to the power negative 34 times 3 times 10 power 8 divided by wavelength is 4.5 times 10 power negative 7 is equal to our work function, which we have got as 3.2 times 10 power negative 19 plus kinetic energy maximum. So we make kinetic energy maximum the what? The subject, and give me the answer. Waiting for the answer.
(1.2 exponent negative 19).
1.2 exponent negative 19 joules. Very correct. These ones, the answers are 2.679 times 10 power negative 7 and 0.4825 V. Okay, we can have this last example. The rest are examples. The rest of the examples, I've sent them on the group. You try them as an exercise. There are quite many. They can be like 8 of them. They'll make a very good. They'll make a very good what? Assignment for you to try out. So we have another number here. Now this one says the work function of tungsten. Tungsten is a metal. Is 4 points. We have the work function of tungsten as 4.49 eV. Ultraviolet radiation of wavelength. The wavelength of UV is 250 nanometers. Do you know what nano is? Nano is 250 times 10 power negative 9 meters. This will give us 2.5 times 10 power negative 7 meters. Then can you check the cutoff wavelength? Cutoff wavelength is got from work function. Remember, if you get work function is HC over lambda, which is the same as HF naught. So if this is F naught, then this one also will be lambda naught. So lambda naught is what we are looking for, is what we can call our cutoff wave length. So with that reason, because they have given us the work function, which is 4.9 electron volts, it will be equal to 6.63 times 10 power negative 34 times 3 times 10 power 8 divided by lambda naught. But we need to convert the EV. Remember, 1 EV is equal to 1.6 times 10 power negative 19 joules. Therefore, lambda naught is equal to 6.63 times 10 power negative 34 times 3 times 10 power 8. All this is divided by 4.9 converted to joules, 1.6 times 10 power negative 19. What answer do we get? The answer we get is the answer for the cutoff wavelength.
Two point 53 exponent
2 point
53 exponent
exponent. Oh, wait, the other one was 4.
negative 7.
We have missed some figure. I know why we have missed that figure. This was 4.49. Have I used the 4.49? I've used the 4.9. So I've missed a 4 here. Please put it there. When you put there the 4, I think the figure changes a little. 2.6, which is the exact answer.
Two point 76 exponent negative 7.
2.76. 67 or 76?
Two point 76
2.76.
Okay.
exponent negative 7.
So it means maybe we interchanged that one. Now, the second question says, find what we call the stopping potential. In those notes I've sent, all those definitions are there. Stopping potential is that PD that reduces the photocurrent to 0. Yeah? So if it's the PD that reduces the photocurrent to 0, it means that the electrons will have lost all their kinetic energy. So it means that the kinetic energy maximum is equivalent to the energy which is exhibited due to the stopping what? Potential. That is the work done by an electron to pass through that PD. You know, when work is done by an electron to pass through a given PD, that work is done by the charge of the charged particle you have times the voltage through which the charged particle is passing through. So with that, you would have got the work done by a charged particle to move through a given PD. So that work done is also energy, which that charged particle can possess. So in that regard, we can have that energy equivalent to kinetic energy maximum, and therefore the kinetic energy maximum is equivalent to the energy which is expended by an electron moving through a given potential, which potential is the stopping what? Potential. So with that note, we can say Ke maximum is going to be equivalent to the charge of the particle times the PD. This PD, we call it the stopping potential. So we shall call it what? Vs. Because the charge is for an electron, so we shall look at an electron whose charge is E times Vs. So to get the stopping potential, which is Vs, you make it the subject by saying kinetic energy maximum divided by the charge of the particle. Now, according to what we have, we can find the kinetic energy maximum from Hc over lambda is equal to the work function plus kinetic energy what? Maximum, whereby we shall have 6.63 times 10 power 34 a negative times 3 exponent 8 divided by lambda, which lambda is the wavelength of the incident radiation. The incident radiation is ultraviolet, and the wavelength is 2.5 times 10 power negative 7. It's going to be equal to the work function, which work function was given as 4.49 times 1.6 times 10 power negative 19 plus kinetic energy maximum. So I can make kinetic energy maximum the what? The subject. So can you get me kinetic energy maximum by crossing it over this side? So we can get that result.
(7.72 exponent negative 20).
7.72 exponent negative 20. 7.72 exponential negativity of 20. This is kinetic energy maximum. So stopping potential can be got from kinetic energy maximum, which is 7.72 times 10 power negative 20 divided by the electronic charge. Charge of an electron is what? 1.6 times 10 power negative 19 coulombs. When you compute, what you get?
Zero 0.4818.
Which is the answer, right? 0.4?
818.
Yeah, which is the answer. Yeah. 818. Okay, approximately 0.482 volts. So that is the stopping potential. Okay, before I can go to something else, we should try out this one. Violet light of wavelength . Violet light of wavelength 0.4 millimeters is incident on a metal surface of threshold wavelength 0.65 micrometers. Find the maximum speed of the emitted electrons. Remember, maximum speed is got from kinetic energy maximum. Eh? So you need to get the kinetic energy maximum and find the maximum speed. So can you give it a shot? Try it out. So I'm assuming you're trying out the number.